Hi class, we are starting Chemistry 112 on Chapter 7, Thermochemistry. So this is going to pretty much cover 7.2. I have 7.1 there because if you look at the list of videos, you'll be like, where is 7.1? I'm pretty much bypassing it because it's usually just a story or something to begin the chapter. So energy. Chemistry is the study of matter, and energy affects matter. What we're going to be dealing with is thermochemistry, heat. Thermochemistry is the study of relationships between chemistry and energy, or another way to say it is the study of energy and its transformations. Energy is the capacity to do work. Energy is something that an object possesses, is an easy way to try to understand that. Work, now all of these should be reviewed from Chem 111 when we did chapter 6, then in that chapter, calorimetry, all the fun stuff that I think most students love about Chem 111. Yes, I'm being sarcastic. I teach 111 lab. I hear it. Okay, so these are just pretty much review. If these are things that you do not remember, I strongly suggest you go back to chapter 6 I believe it's chapter 6 if it's the same book I had, and look this over so that you get comfortable with it. Because the one thing about 112 is the same as 111. When you come in from the previous chapter, it's with an understanding that you retain that information from that previous course. Now, in reality, is that really true? Not always, but then you have to make the effort to make sure that you stay on top of this. It makes it easier on you. So, work is the result of a force acting through a distance. It's energy resulting from a force acting on an object over a distance. And a good way to think of this is pushing a box. You're doing work on the box. The box pushed across the floor, work is being done on it. And then heat, which is Q, is the flow of energy caused by a temperature difference. So heat is, if you think here, heat will flow from where it's hotter to colder. So if you know for instance, let's say the room temperature, it may be a very small room, you know the initial, and then once the heat flows, you will know the final. There's a temperature difference that has occurred because the heat, energy in the form of heat, has spread out to the surroundings away from the system, and the system in this case being the coffee cup. Same thing as for an endothermic, you have a temperature difference of the surroundings, which is outside the icicle, and the system inside, and you can tell that there's a temperature difference from before the heat started to go into the system and before. Did I say before and after? Final minus initial. Energy can be exchanged between objects through contact. For example, through collisions. Your book talks about pool table and pools. That's a perfect example how energy is transferred from one object to another. So again, this is mostly review, but we're going to start expanding on this. Kinetic energy is the energy of motion. That's pretty easy. If you think of motion, that's kinetic energy. Potential energy is basically related, the potential, and it's just what it says. It's potential energy related to its position of where it is. Or another form of potential energy is food. We eat food, that's stored energy that will be changed to kinetic energy. You can't run a marathon on, Snickers. I know the commercial probably says you can, but good luck. And so it's energy, it will change from potential to kinetic. But there is, we're going to cover in the next few slides, law of conservation of mass, something that's also been talked about in Chem 111. Energy is neither created nor destroyed. There's a certain amount. And this roller coaster gift that I put up is a perfect example of that. If we had numbers to this, you would see that the sum of these total energies is a certain amount, and that number doesn't change. What has to change in that is the potential energy value and the kinetic energy value. So they go up and down, but the total sum number has to stay the same. So I want to take a look at this little roller coaster here, which I think is really cute. Potential energy related to its position. So you see it gets to the highest when it gets to the highest peak, and then it loses and it transfers that energy to kinetic, and then as you see, kinetic starts going lower when the potential is highest and vice versa. Thermal energy is the energy associated with temperature, heat. Just think of heat. Thermal energy is a form of kinetic energy. Manifestations of energy. This is just a breakdown. Kinetic energy. Energy is the capacity to do work. Well, we have two types. We have kinetic and we have potential. And kinetic energy, motion. Just think of motion. If you're moving, that's kinetic energy. If you're not, you have a potential energy. Thermal energy is associated with temperature. Temperature differences is more to elaborate on that. Potential energy is due to position or composition. Position is, for instance, a dam. All that energy that is being held behind that dam will change to kinetic energy if that dam breaks, and it could be very, very powerful. Chemical energy has to do with unstable compounds. TNT is a perfect example of an unstable compound. It has the potential to give off an explosive amount of energy because of how unstable that compound is, and that's what happens with unstable compounds. They actually want to get rid of this excess energy to go to a lower state. Chemistry is all about stability and everything trying to attain the most stable, lowest state possible. Conservation of energy, this is what I talked about. The law of conservation of energy states that energy cannot be created nor destroyed. You know, you see a lot of things in movies, but there's always got to be something that is taken from somewhere else or gained somewhere else. When energy is transferred between two objects or objects converted from one form to another, the total amount of energy present at the beginning must be present at the end. You may not be able to always see it with your naked eye, but everything has to be accounted for. What this means is that it's basically energy is transferred. You cannot see it always, but it's being transferred. So if energy is lost by a system, it must be gained by surroundings and vice versa. And the system is, think of our experiment. It might be going, or for instance, a coffee cup. The heat will go into the surroundings, or if it's an endothermic, the heat will go from the surroundings into the system. But something is always transferred somewhere. System and surroundings. So here is a perfect example. We define the system as the material processes within which we are studying. It's really easy to define this as an experiment. Whatever your experiment is on, and even then you have to define what part of that is your experiment. For instance, here if we look at this flask, Erlenmeyer in the system, is the system just the solution itself, or is the system the container and the solution? You have to be able to define what these are. And then once you define, for instance, let's say that for this case, the system is the beaker and the solution, then that means that everything outside of the beaker and the solution is the surroundings. And put those together and that equals the universe. So when you understanding the boundaries of what is the system and what is the surroundings, it kind of helps you to understand when you start looking at work and heat. So conservation of energy means that the amount of energy gained or lost by the system has to be equal to the amount of energy lost or gained to the surroundings. Just what I've been saying. You can take a look at these gauges. So if you look at the before, here, before energy transfer, you see it's half. Think of this as a gas tank. It's pretty easy. Think of this as half. The tank is either half full or you could say it's half empty depending on how optimistic you are. And what happens is that after it goes through a change, you will see that it's lost a quarter of it. Well, where did that quarter go? Well, if this is the system part, that part that left has to have been transferred, and it has to have been transferred to the surroundings. And it was, because you see, this is half, this is a quarter. Once it's been transferred, you see that now the system is a quarter, and the surroundings has taken up that energy of transfer, and now it's half. So units of energy, we are going to use joules, but you need to start out understanding one of the other things first. So the amount of kinetic energy in an object is directly proportional to its mass and its velocity, which is its speed squared. So the definition of that is 1/2 mass times velocity squared. Why am I introducing this? Because you need to know the units for that. And the units for that are kilograms times meters squared over seconds squared. And remember, seconds is not SEC. That's wrong, and I would mark you wrong. It is an S. And that is also equivalent to 1 joule. So these can be converted very easily. 1 joule equals 1 kilogram meter squared over second squared. And joule is the SI unit for energy. Okay, so let's do an example. A pitcher throws a baseball with a mass of 5.13 ounces, which is 0.14 kilograms, at a velocity of 95.0 miles per hour, which is 42.5 meters per second. So we have, first of all, we need to determine where our mass is, and it pretty much spells it out here. It's given to us. And our velocity, and it's given to us. So we need to know, we need to be comfortable using the equation for that. And then it's asking for, in the second part, we need our answer in joules. So we need to convert this. So we pull out the information that we have. We plug it in to the formula, which is seen here. And it gives us 131 kilograms meters squared per second squared. But we're not done because the answer needs to be in joules. So once we transfer it, which you really didn't have to go through this, but in case you guys have forgotten how to set stuff up, this is why I'm doing it. And like the rest of the chemistries, sig figs follow. You do not want to have you go through all this hard work and then have your answer counted wrong because you didn't follow sig figs. So 3 sig figs. 3 sig figs, this is multiplication. Multiplication has to do with the rule of the smallest value dictates the significant figures. Remember, this is equal, so we're not going to count that. It's 1 to 1. And here we go. So 131, 3 sig figs, that's our answer. Okay, so let's expand. A joule is the amount of energy needed to move 1 kilogram mass a distance over 1 meter. There's also 1 Newton per meter. That tends to be more physics, so I'm not really sure why this is in here, but we'll find out in future chapters. And so all of these are equivalent to each other. Now let's take a look at calorie. Calorie is also something that you should be familiar with from Chem 111. Small c, calorie, and then there's big C, calorie. This tends to be for nutrition, this big C here, but you need to know both of them. So 1 calorie is equal to 4.184 joules. That is a conversion. This is an equality. Here's another equality. 1 big C, calorie, is equal to 1,000 calories, or 4,184 joules. And 1 kilowatt per hour is equal to 3.60 times 10 to the 6 joules. That was mentioned here, though I kind of bypassed over it. 3.6 times 10 to the 4 joules, or 0.01 kilowatts is used in 1 hour, which really doesn't give more of a story than that, so we're just going to move on from that. Okay, so here is a chart of, you can see what units, amount required to light a 10-watt bulb, amount used by a human body running a mile, and amount used by an average U.S. citizen in a day. Now let's get back to conversion. So convert 685 big C cal. So you need to make sure you understand what big C is and what little c is to joules. You need the conversion. 1 cal, big cal, is 4,184 joules, and then we set that up. This is 3 sig figs. So we have 3 sig figs, and this is entered in scientific notation. But what if we want to convert from kilowatts per hour to joules? Same thing. We need to make sure we have the conversion for that. We set it up. Units that we want to get rid of on the bottom, units we want on top. And here's another scientific notation answer.